Hello and welcome back to another episode of Mathsplaining Science, where two nerdburgers sit down and talk about science through maths. I have with me here the incredible Nadia, my partner in crime, and my name is Catherine, and we're both ex-teachers, and we just want to kind of talk about the classroom and, have some fun trying to collaborate the two subjects together and figure out how we can do it better. Bro, how's your week been?
I had COVID. I didn't tell you. I did. I did not tell you. I just realized this morning I didn't tell you. So hopefully my voice doesn't sound too nasally. I was out of action for an entire week. And after I kind of recovered enough to get out of bed, I am now like trying to push through. I'm going to blame COVID for the reason I struggled with today's question.
All right, I'll take that. That's the one excuse I'll take. That brain fog.
Yeah.
100%. Okay, speaking of that question, what are you feeling better though before we keep going?
I am. I'm still a little bit headachy, and you know what it's like recovering from a cold, let alone a flu. So I might get into parts where I'm just like,
no, that's all right. That's what editing's for. Yes, you wouldn't believe how much we have to edit out because of the crap that we say to each other.
Oh my God. I have a bit of a potty mouth, so I'm very sorry. I cut it all out.
Yes.
How's your week been? Okay,
we need to sound professional, We need to sound professional.
I know.
Just a normal dude. We had someone visit from the States that I haven't seen for like 30 years, so I don't really remember him. Come over and visit, and I didn't know they were coming, so that was cool. He came over to Melbourne, and Nan took him around, which was cool. And then he went back yesterday he went back to Sydney. He went to Sydney to go see my uncle and surprise him. So that was really nice. It's really nice to get the family together.
You got such a great family. That's why I'm paying your mum to be my mum.
Do you know what? You don't know that until you get older, but I'm so incredibly lucky with a family that it was like a lottery. Your family's like a lottery. You don't get to choose them. Yeah, but I'm grateful for family and some of the family practices we did when we were younger that I thought was just such a drainer. Like, we had dinner with each other every night. And then it just became normal. And then I didn't know that that wasn't common practice for families. And then reflecting on that, I'm like, oh, okay. Right, that's what brought us together, and that's where this is coming from. So even though 3 of the 4 kids have kind of moved out, every Sunday we come back and we have family dinner, just because that's what we've always done. Yeah. So no, I'm really incredibly lucky that I have such an amazing family. Don't tell my parents I said that though. Lol. For this week's question, I sent you one that was, in my opinion, was just like entirely maths, and it was about dilution. Now, no matter how many years I've taught this, how many different ways I've taught this, students conceptually still don't understand what dilution means and therefore struggle to calculate it. And this type of question sits nicely with a few of the analytical techniques in chem. Therefore, there's a high chance that it's assessed every year, and because it's that last question that separates the really high students from the high students, So the students will get, to like part 3, part D, and then part E is like, oh, what was the original before you diluted? And then that's when most of the kids kick off. So I thought I'd kind of hit you up about it to see what it is that I could do to better support kids with this type of.
Well, you really did kill me with this one. I don't know. Again, blame COVID. I don't know. No, I don't actually. This was a tricky one, and I'm not adverse to admitting when something has gotten me. I don't know why I struggled so much with it, but I just could not get my head around it conceptually. And in the end, I kind of figured out what the issue was, and I'm going to discuss it with you. I'm just going to bring the question up.
You can't get it. Like, how the heck am I expecting my kids to get it? I just think it's because I've done it so many times. I'm like, oh, it's this. And then not appreciating the complexity when you come across it.
I just couldn't believe it was worth 2 marks. That's what, no, it was worth The first part was worth 1 mark. The first part was
that was easy.
pretty straightforward.
Yeah.
It was that second part. Oh my God. There was one part of it that just kept stumping me. So I'm actually going to tell you what I think I
show me what you
had the most problem with. So the first part was very much just a reading off the graph.
Yeah, 100%.
You had to determine the sucrose content of the sample in grams per litre, which was fine, and it told you that the sample, those used to determine the calibration line, was found to be 1900. So obviously I kind of just went, okay, 1900 is around here. So we ended up at 0.3 grams per litre.
See what I mean? This is meant to be a chem question, analytical chem questions.
Yeah.
You don't have to know chem to answer that question.
Yeah, that was easy. 1 mark.
And
easy
neither
one.
the next one. But anyway,
and that when I looked at the average people that got it right, was quite high, like 70%.
But so my thing is that should be 100.
That should be 100.
Literally lining up two sort of coordinates and bang. That's the stuff that you learn in year 7. And that's a linear graph.
Why do you think they didn't get it right? Because I really looked at this question and like there was so much stuff. Like I think it was overwhelming. When you first sent it, I was like, dude.
Yeah, I remember.
I can't. And then
I was like, just trust me. I was like, just trust me, just read it.
Give me a minute. And then I figured it out. Like the first part, I was like, okay. But because do you think it's because of the sheer overwhelming pieces of information that are in here? Because if you take a look at it, you've got all of this information. Right. So it's all of this information, all of this information, all of this reading over here. And then, I mean, really, we don't need this table here at all. We really just need the graph, right? So it's almost like they're trying to trip the students up. So maybe they're not, but I think the first thing that students will need to know is kind of like what we do when we do NAT plan and multiple choice questions. We're like, okay, what information is necessary and what information is not necessary in this question, and then just like scratch it. Don't even look at the unnecessary pieces of information. So that's almost the conversations you have to have here.
You look at it though, the volume of information, I would agree with you, the volume of information presented versus the volume of information that's discarded after you figure out what you're doing is so high, right? But you have to be able to get through that first. So some students will look at this, and I'm sure it happens for every subject. Like biology is prone to doing this, where they write slabs and slabs of text. They might chuck a graph in there, and then by the first impression, kids like, nah, can't do it. And then have to force yourself to go through it and read it and deconstruct it before you even get to a question. Oh, well, that's half the battle. So realistically, the maths in here is year 7 level maths for part AI, where you just have to read a graph.
Yeah.
According to the curriculum.
According to the curriculum. Well, I'd say, year 7, year 8.
Linear graphs and reading from a linear graph is year 7. Okay.
Year 8.
So
around year 8.
Okay, let's go year 8 then. I'll give you grace, a year's grace. That's 4 years worth of, that was 4 years ago. Then assuming that the kids learnt it the first time and built upon it in the next 4 years. So hit me up with part AII. So I think we have to, for that part, we probably need to go through the question stem first. So people kind of understand what's going on before we actually talk about what it is.
Okay. I have PTSD.
Did you draw it out for yourself the first time? Like, did you draw a diagram?
I did. The first time I looked at it. Okay, so I'm going to unpack it first. So because I knew that we had 0.3 grams per litre. And can I just say, it was the grams per litre. It was this concentration. This is why I misunderstood a lot of what happened. I got this question wrong multiple times before I got it right.
Okay.
So what I did first is I drew out 100 milliliters. And so we started off with 5 milliliters
Yep.
of the soft drink.
5 mils. Yep.
5 ml in 100 ml. So we've diluted. So we
Sure.
diluted that.
Mhm.
And so this is how I did it first. So I worked it out as a percentage. So I worked
Sure.
out 5%.
Sure.
That's going to be 5% of
Mhm.
soft drink.
Mhm.
5% of soft drink. And then
Sure.
I drew out 250 ml. So I just made it bigger. So this is 250 ml, and then they added 10 of the solution into that.
Mhm.
Right, so that was 10 milliliters in 250 milliliters. So
Okay,
I
so to confirm, it's the 10 mils of the 100, right?
of the solution, of the 100 ml solution.
Right. So when you diluted it the first time, you then took 100 mils of that dilution over to another cup.
Over to another cup.
Okay.
Yes. So
Okay.
it's doubly diluted.
Sure.
Correct.
Mhm,
Okay.
mhm.
Then the way that I visualized it, and I think this is where, so I think I did it right up until this point. So I kind of worked that out to be around 4%
Okay.
of.
How did you do that?
So 10 mil of 250 mil.
Yeah.
So I just went 10 milliliters
Mhm.
out of 250 milliliters.
Mhm.
That's 1/25th. So 1/25th of that 250 ml solution now is from that original 100 ml solution.
Mhm.
Yeah. So that works out to be 4%. Now, probably in hindsight, after I went back and did it, probably would have been easier for me to keep it as a fraction, but I changed it to a percentage. So I said that's the way that I work with percentages is I literally just do this. I just change my denominator and make it 100. So I multiplied that by 4. So it's going to be 4 hundredths, which is 4%. Okay, so 4% of that solution is from the original solution. So this is where my mind went off on a crazy tangent. And I think I overcomplicated it because then I went, well, 5% of that 4% is my soft drink. Soft
Sure.
drink.
Mhm.
I don't know. It's just, yeah.
Mhm.
It's kind of like saying, this is my ear. Like, why would you do that? But anyway, I did that. So then I'm like, okay, 5%, 5 hundredths multiplied by 4 hundredths. That's going to be 20 thousandths, which is going to be 0.02, which is going to be 2%.
Okay. 0.02, 2%. But you're talking about a volume, aren't you? So can you describe to me what this 0.02% actually represents? What are we talking about here?
No.
Oh, cool. Awesome. Okay.
Now I've confused myself. This is how I did it to start with. I'm like,
Right. Right.
what is that? I went through this process and I ended up getting something like 600 grams out of 1,000 mil. And I was like,
that's
a lot of sugar. Unless it's slurm. I don't think that's right. Do you know what slurm is?
No.
That's all of our Futurama fans out there. So there was an episode of Futurama where there was a big worm and it used to anyway, slurm. So it was a very concentrated drink.
Okay.
But no, 600 grams out of a liter, that doesn't sound right. So I scrapped that quickly.
Sure.
It's a lot. But this is where I really struggled.
Okay. All right.
But
so
then
how did you solve it the second time?
Okay.
So you're like, you sat here and you're like, I don't know what this 0.02% actually represents. Okay. No idea what the flip is going on. I'm going to try it again.
So the second time I took my 5% solution and I recognized that was 1/20th. And so 1/20th of my 100% is soft drink. And then, so we've broken up into 20 parts. That is 1/20th. And then I took my 250 mil and then I took my 1/20th, and that 10 mil now is 1/25th.
Okay.
So I then took my 1/20th of my 1/25th,
Mm-hmm.
because it's a fraction of a fraction, and I got 1/20th times 1/25th equals 1/500th. So 1/500th.
Hang on. Sorry, I'm going to pause you there.
Uh-huh.
How is that number supposed to be any different than what you did before, the 4% of the 5%?
I think it's the same,
Okay.
but I think it was me converting to percentages and back and forward and back.
Okay.
That's where my mind was just like, I'm losing track of what I'm doing here.
Okay, got it. Sorry, you keep going.
Yeah, but with the fraction,
Mhm.
I kind of understood it.
Okay, because essentially, if we convert that to decimal, that's still 0.02.
Exactly. 1/500th of the 250 milliliter
Sure.
solution is the OG soft drink.
Okay.
This is where I started getting confused because of the conversion between milliliters and liters. And that's where I think that's where, because there was just such an intense cognitive dissonance that was going on in my head. I could not, I don't know why, it just got me. But I went, okay, 1/500th of 250 mil is 0.5 mil.
Yeah.
So in that 250 mil, there are now 0.5 milliliters of soft drink. So that's the volume.
Okay. Yep.
Of soft drink.
Yep.
And then that concentration of soft drink was 0.3 grams per liter. So then I multiplied 0.5 by 0.3 grams per liter, because if we have 0.3 grams per liter, the liter, and this is where it started to get confused, because it's per liter. So I couldn't just convert the 0.5 mil first. I don't know why. But then I did this.
Okay, yeah.
And I got 0.515 grams per milliliter. Per milliliter.
Interesting.
And then I multiplied that by 1,000. And I got 150 grams for every liter.
What's the answer? What's the answer?
That was the answer. That's in the 250 though.
Yep.
That's in the 250. So not in the original. So that's for every 1,000. That's the difference. Okay. So
how do we then get it to?
For every 1,000. In that 100 liters, we have to divide by 10. So then it's 15 grams in the 100 milliliters, which equals to 15%.
Okay, interesting. I want to swing back to your calculation at 0.5 times 0.3. So that we said that we had 0.5 mils, is that right? Of the soft drink. The unit is 0.3 grams per liter. So that's like for every 1,000 mils, I've got 0.3 grams, right?
0.3 grams for every
liter.
Every liter.
Yeah.
Every liter, yeah.
So if I go down to the mils, then I'd have to divide that by 1,000, right? To get to, okay. So 0.3 divided by 1,000 is 0.0003 grams for every mil.
Yes.
Mil. Okay. If that's the case, in 0.5 mils, I should have half of that, which is 0.00015. True?
Yeah.
So how do we get from that value to 15%?
I don't know.
All right. Let's try and thrash this out. I'm just going to get a copy of the question, because this is doing both of our heads in now.
It really is. This is what I think I just completely confused myself.
But you know what? They expect you to do it, and it's sold as if it's really easy.
11% of students got this right.
This is what I'm telling you. Unbelievable. Okay. All right, let me share my screen. So we think about it, a few things. Let's break this down a few times, a few bits and pieces here. So I left the graph here just for argument's sake, just so we can see for referring back. But you established based on you reading the graph in the first question that we had 0.3 grams per liter.
Yeah. Mhm.
The percentage of mass. Now, mass volume, that's cool, in the 5 meter sample of soft drink. If we were to draw the soft drink like you were doing, so we have 5 mils of soft drink. Okay. We got 5 mils, and it was made up to 100 mils, is what you said. Right. So this whole thing is 100 mils. Right.
Love that your drawings.
Oh,
Hey, I forgot her stylus.
oh no, I forgot my stylus, and now it looks like
Prepared.
I know. I'm calling in from work, my lunch. All right. So we'll take 10 mils out of this,
Mm-hmm.
and we chuck it in the 250 mils.
Mm-hmm.
So it's like make some sort of really huge ass container. So this is go up to 250. Okay. And it was the 10 mils from here.
Mm-hmm.
Which is right, which is exactly what you've drawn. Yeah?
Yep.
Okay. And then whatever. Okay. Now when we did the analysis was from sample solution was from here. Right? So what we're saying, this value here, 0.3 grams per liter, is the concentration of this here is cool. So it doesn't matter how, now, if you could have taken 20 mils out of that, you could have taken 50 mils out of the 250. Conceptually, the concentration never changes. It's like saying, when you have a bottle of Coke and then you pour it into a cup, does the Coke taste the same? It does, right? So that's suggesting that the concentration of the Coke in the bottle and the concentration of the Coke in the glass is the same.
That's a good analogy.
But what's different about it is, if we're referring, let's say we refer to sugar, the amount of sugar though in a 1.25 liter Coke and 250 mils cup is very different. But relative to the volume, it tastes the same. So concentration is essentially how much stuff you have in your given volume. That's it.
Yeah.
Right. So however many particles of that thing in whatever mils you want or whatever volume unit you want to use. So if we then just look at the 250 mils and we go, okay, in that 250 mils, the concentration is 0.3 grams per liter. I know I don't have a liter though. So in terms of the grams, how many grams then, if I have 0.3 grams per liter, how many grams should I have in 250 mils? That will give us what's in here.
You know what? Okay. Yeah. Oh my God.
So if that's 1 liter, then, and I do my calculation, then in here, there should be a quarter of that?
Quarter of 0.75, I think.
Yeah, 0.075 grams per 250 mils. That's what we're saying. So that has to come from the original 10 mil sample.
Yep.
Okay. So what we're saying from the graph, and the graph was taken out of the 250 mils, which is beaker number 2. Actually, I'll use a different color. Okay, this is beaker number 2. This is beaker number 1. Okay. So that's saying that the concentration of the 250 ml solution is such that for every liter that we would have, there would be 0.3 grams of my stuff, my sucrose, my sugar in there. But I know that here, I don't have 1 liter.
So you divided it by 4.
By 4. Because I know that if there's 0.3 grams in a liter, then there's got to be like a quarter of that in 250 mils.
Gotcha.
Yeah. And that could only have come from my sample.
Okay. So you've divided 0.3 by 4. 0.075.
So 0.3 grams per liter. If you want to do it from a mathematical perspective, it's like how many grams do I have per 250 mils? That's what we're asking. And to do that, we divide that by 4. So that equals to 0.075 grams per 250 mils.
Oh my God. And then you figure out how many is in 100 mil. And then you just work it out as the percentage. Why was it so hard for me to understand?
I think this is the one time you needed to connect visual, like and conceptual visual, and the mathematics. Because if we were just playing with numbers and we started to get lost as to what each of those numbers represented. I think that's what happened. And so here, as I'm drawing it, I'm showing you my thinking of the calculations that we were doing to give context to those numbers. Does that make sense?
Yeah. You know what I think this is where the juxtaposition of maths and science needs to come in, because I needed to understand a little bit more about concentration, because you explained it beautifully in the Coke analogy and it just made sense. So from the Coke analogy onwards, I was like, of course. Right. And then just visualizing it, of course, 250 mil is a quarter of, like, it's all relative. The concentration hasn't changed. It's just the volume of sample has changed.
So what hasn't changed is how much you, let's draw an example, just to kind of like bring the point home. So here, let's go from this dilution over to 2, right? And the second dilution. So let's just say, for argument's sake, I'm just going to draw something arbitrary. So in glass number 1, right? Yes, it's 100 mils. Okay. But let's just say I've got 10 of those, like each of these circles represents sucrose. Again, arbitrary number 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm just making it 10 to make it easier. And then we go over here and we say, I'm going to take 10. Right? So essentially we're saying, because we're talking about solution is implying that it's evenly spread. So we assume that if I've got 10 of those like blocks, if you think about blocks of sugar that we used to put in tea and coffee, so let's say there's 10 of those blocks in there just floating around, right? So if I take a 10th of that, and if I've got 10 of these, essentially I'm just taking 1, right? And I put that 1 in here, but I make it up to 250 mils.
Yeah.
That's the relationship. So the relationship is, you take that 1, there's still just 1 in here, true?
Yeah.
But you make it up to there. So the concentration has changed, but the amount that you took out of here that you put into here is the same.
And then yeah.
And then when you go back, so so the concentration is, now this is like 10 over 100 as an example, right? But now this is 1 over 250 as an example, because that's how you calculate concentration. It's like how many of those sugar molecules there are in that volume that you've got. So what's different is that the concentrations have changed. What's the same is the amount that you took out hasn't changed. You took out 1, so it's still just going to be that 1 in there. So when you go backwards and you go, okay, I now know that it was 1. So I'm going backwards now. I know that I actually only took 1 particle out. And I know that 1 particle had to make up 100 mils, right? Had to come from 100 mils. So there's 10 times as many in the 100 mils. That's where I originally got it from. There's 10 times as much in total. And this could only have come from your 5 mil sample, because that's where the sugar came from. The rest of it's water. That's the hard part. The hard part is proving to students that concentration changes, yes, but sometimes when you dilute something, the amount of stuff you have in there hasn't changed. So for example, the amount that you had in here and the amount that you had in here is the same. So I had 1 particle in here. I had 1 particle in here. It's the same. But when you put it back in the whole thing, well, you know that there's 10 times as much or something like that. Does that make sense? You've taken it out of that.
Yeah.
And knowing that all of that sugar could only have come from the 5 mils of Coke that you put in there originally. So when we do like the chemical formula, we go C equals N over V. Now concentration represented by C. N is like the particles, the number of those particles, and whatever volume you have. Right? So realistically, we should be comparing the 10 mils and the 250 mils. That would have been an easier comparison. 10 mils and the 250 mils. What's different about them is their concentration, right? Because when you go from that 10 mils and you dilute it to 250, your Coke tastes different. Your cordial tastes different. But the original amount of sugar that you had has never changed from the 10 mils and the 250 mils. It just tastes different. So what that means is the number of stuff that you have, so just say N1 and N2, they've got to be equal to each other. Because if I had 1 sugar particle here, I'd still only have 1 here.
Yeah.
Right? If I had 2, I'd still only have 2 here. So the number of particles in that sense has got to be the same.
Mm.
When we rearrange this to find n equals CV, isn't it? So we're saying that n1 equals to n2. It has to. Essentially, what we're saying here is CV1 has to equal to CV2, C2V2. That's when the mathematics comes into it. Because conceptually, the 10 mils, whatever's in 10 mils and then whatever's in 250 mils in terms of the number of particles is exactly the same. It's just a different concentration.
Yeah, but you're not using up all of the, because I think this is where I got a little bit confused with the whole thing, because first of all, I forgot that, like, I just didn't even occur to me that the concentration is spread out in that entire 250 ml of liquid.
Yep.
Do you know what I mean?
Sure.
Like, I was still trying to visualize it as it is a concentration of a fraction of a fraction in terms of concentration, but really it's the concentration is of the entire amount, the entire volume. But also you've started with 100 ml, and if you had a certain concentration in that, you're still only taking 10 ml of that and you're adding it to the 250. So you're not going to have the same amount of concentration.
Yeah, you're not going to have the same concentration. Yes, correct. There's two ways of looking at this. You can follow the whole thing from a concentration perspective. So we can say, okay, we had 5 mils, most concentrated. Went to 100, okay, dilute. So we diluted by a factor of 20. And then we diluted it again. So even less concentration before, right? By a factor of 25.
Yep.
So if we go backwards, we just go times 25 times 20. Right?
That's what I was trying to do.
Yeah, right.
Which is what you do. Except my brain was turning to mush in the process of that whole thing, because I was trying to go forward instead of reverse engineer it. I was trying to imagine what was happening in the process of the concentration as we moved forward. But in actual fact, what would have been easier would have been to recognize that in that first fraction, when we diluted it, it was diluted by a factor of 20, like you said. And in that second one, it was diluted by a further factor of 25. And then just worked backwards and said, okay, well, we ended up with a concentration of 0.3 grams per litre. And then you're just using the proportion of dilution. So you went, we diluted 25. So you multiply the 25 first, that brings you to the 100, and then you multiply it by 20, and then you end up with 150 grams per litre of.
And how many do you have in 100 mils then?
So therefore, in 100 grams, so you divide it by 10, because 100 millimeters is 10% of 1,000, and so then you get 15 grams.
Yep, per 100.
Per 100.
Yeah.
That's so much simpler.
Totally.
See, it was.
Totally. So let's draw that conceptually before we lose it. Yeah. So we went from actually, maybe you draw it because you've got your stylus.
Yeah, okay. All right, let me share.
But you see what I mean? If you take your reference point from concentration, it makes sense. But if you take in chem, there's two ways of doing that. Either you look at it like moles. The kids could have calculated mole if they really wanted to, and then follow that from an amount in mole perspective, or they could have recognized it in concentration. Okay. So now you understand, like, it's much easier than you think, right?
Yeah. Yes.
So you draw it again, and we'll go through it.
So here's my 100. This is 1/20th. So 1 part for every 20 parts.
Yep.
And then we've gone to 200. So this is now, and that's 10 milliliter out of 250 milliliter. So 10 mils, chucked it in there. So we've got 10 mil now. All right. 10 mil in 250 milliliter. So that is 1 part for every 25 parts. Okay. Now, for this concentration, they tested that solution, 0.3 grams per litre.
Yep.
like that. So that was after it had been diluted twice, right? The first part, 1 in 25. The second
Oh, 1
part,
in 20, yeah.
1 in 20. So to work backwards and to go back to this, we have to multiply by 25.
Yep. So what you're saying there is, okay, it's 25 times more concentrated because you had to
Yes.
dilute it 1 in
Yes.
25. Yeah.
25
And that's
times
why we're
more
multiplying by
concentrated.
25.
But then we have to multiply it by another 20.
Yep.
To get how much sugar is in our original sample.
Which is the 5 mils.
Which is the 5 mil.
Yep.
To get to the 5 mil.
Yep.
So we multiply by another 20 and we get 150
grams per liter.
Grams per liter here.
Yep.
But in 100 liters, because we've only got 100 liters over here.
100 mils.
Instead of 1,000, we divide then by 10.
Yep.
So we would then divide this by 10 because 1,000 is a tenth. And we get 15 grams per 100 milliliters in our 100 milliliters, which as a percentage is 15%.
Yep.
Wow. It took two professionals an entire podcast. How do they expect these students to so I had the solution, just as a, full disclosure, but I didn't want to figure it out mathematically because in my opinion, I want to know what's actually happening. I want to know because I was struggling with the whole not understanding, the whole concentration, not really being familiar. I mean, I kind of fundamentally understood what concentration was, but not really having thought about it too deeply, was having to unpack the idea of concentration, try to visualize what that meant. And that's where I think I just couldn't do it. But looking at the maths and how you explained it mathematically, like C1, C2, N1, N2, I could have, if I had done this question before, I could have recreated it. But now that I understand about concentration, I think I could probably solve another problem like this a lot quicker and a lot simpler without having to rely just on the formula.
Yeah, and that's the thing. So VCAR is expecting that the students start from the formula, which is, C equals N over V. And then they expected them to recognize that the number of particles between like the 10 mil sample and the 250 mil sample has never changed. And so really, if it's N1 equals N2, and we're substituting the formula, it's C1 V1 equals C2 V2. Do that again, right? You do it a couple of times. And so that's where they get stuck because they jump straight to that. And conceptually, they don't actually understand what happens when you dilute something versus what happens when you just take a sample of it. So, it's the whole, I pour it out from a 1.25 liter bottle into a cup, tastes the same. But if I put more water in the cup, it's going to taste different. But the amount of Coke that I had is still the same. I didn't add any Coke. I just added water. And so that concept doesn't sit well with kids. And therefore they come in here and they go straight to the formula and it sucks.
So when you're teaching this concept, did the students get given the formula? Did they get given a formula and taught how to transpose the formula and then substitute all of their variables or their unknowns in, etc., and solve it that way?
Sure. There's two parts to that question. Me as an individual versus me as general teacher. Right? So I would say that general teacher will go, well, kids already know C equals N over V from year 11. So let's introduce it like that. And then we'll use the formula of dilution. Me as a personal individual, having gone through all of that crap before, goes, guys, what happens when I do the Coke thing with my kids first. Yeah. Then I prove to them that N1 equals N2. And then I use the formula that they already know and I just manipulate it and go, well, if it's N and when we look for N, it's C times V. Well, this C times V has got to equal this C times V. So that's how dilution works. Yeah. So I have to. Otherwise, it doesn't make sense. And then they just use that formula for anything. And I'm like, that doesn't make any sense. But yeah, so they learn it as C1 V1 equals C2 V2.
But
which
you
is
can
why
see, you can kind of see how the understanding of the chemistry, that the concentration is so necessary here, because if they have that understanding of that, this is what happens in the Coke. I mean, I know that it is predominantly mathematics. Like, you don't have to have like you don't have to have a degree in chemistry to understand how concentration works.
Yeah.
But they do need to have that background of concentration in order to even be able to unpack. I mean, I didn't need that formula, clearly.
No, you didn't. No, you didn't.
To do it. So it can be done without chemistry knowledge if you had that basic understanding of concentration.
Yeah.
Yeah. But you really need to have a deep conceptual understanding and have that practice in these solving these types of problems without just being given a formula, right? Because if students don't know how to sit with a problem, like I sat with this problem for close to 2 hours because my mind just was not getting it. But in the end, I got it, and then I lost it after an hour. But talking through this whole process with you again, because that's what I would generally do, right? And as a student, that's what you want them to do. So you're teetering kind of on the edge, and you don't want to quit, because you know that when you're in that learning pit, that state of confusion, that's when you know you're almost at a breakthrough. Don't quit when you're at that confusion phase. And that's when I would suggest that you go discuss it with someone, because just me having the conversation with you, it was like a light bulb went off. And I think that's where that dialogue and that collaboration becomes really important. I think that this was really good.
This is a good question.
This is a good question. And
too bad it's only worth 2 marks.
it's
pretty crazy. It's pretty crazy if you unpack it, as you can see, this is what you had to understand for yourself at every step.
At every step.
Yeah.
I mean, I know that kids have, if you've done a chemistry course, you'd be, exposed. So this is my first exposure to this question, and I struggled with it. And I'm hoping that, students have had more of that exposure. But I'm actually thinking, if a student did sit with this question and took a whole lesson, a whole class, to just really understand it conceptually rather than have the formula, it would it's so worth it, because they would then literally be able to solve it without worrying about the formula, just understanding what's actually happening within the concentration system, right?
Yep, there's got to be a better way to teach this. I'm still trying to find it, but there's got to be a better way. But yeah, look, thank you for indulging me with this question. When I first sent it to you, I know you were like, nah, sorry, mate, because I gave you a slab of text and you're like, how am I supposed to be able to do this? Yeah. But thank you for sitting in that pit with me. I think it's lots of learnings for us both from both science and maths.
Yeah, it was great. Thanks for like pushing me over the edge with this one, KR.
Oh, you had it. It was just like there were too many numbers and too many steps.
Yeah. You did challenge me on it, so good job. Keep throwing them at me and see how many you can trip me up on. This is number one, numero uno.
Nah. Look, I really appreciate the fact that, we could have made a different decision. You've done the question. We could have just gone straight into, let's just go to when you figured it out and we'll move forward.
I think it's so important for people to understand that even at any level, you're going to get questions wrong. And like I said, I got this wrong. And I couldn't figure out, like I kept getting the same answer and it was the wrong answer. And I couldn't figure out where I went wrong. And eventually through this discussion, I 100% get it now. So I think these discussions are important, and it's important for everybody to know that.
I appreciate you being right away. It's great. All right, mate. Thank you so much for your time. I know we've gone a bit over time, but yeah, until next time. The words of wisdom without any profanities this time.
Yeah, I did say a swear last time. We had to edit that out. Words of wisdom, honestly, I've already said them. Don't always expect, even in front of the students, we are human, and we need the students to understand that as humans, we're going to get things wrong, because the stress that comes and that's associated with these types of situations, if all of the kids know that it's okay to fail and that we embrace our failures, but we don't let them stop us, we use them as stepping stones and steps to success, that's the most important. Don't give up.
Awesome. Well, thank you so much for joining us today. We hope that you learned something new as well and thrashed it out with us. If there's anything that we can do to support you, please let us know and we'll do what we can. Otherwise, until next week and another crazy mathsplaining question, take care and we'll see you soon.
See ya.
Bye.